Mrs. Patel Dame here. We are in the home stretch of Unit 9. So this kind of wraps up some stuff with energy and something called entropy. And yeah, so it is the final unit of AP Chemistry. So entropy, some of us know this better than others. This is disorder. So if you think about, like you go to school, you have practice, you have work, etc., etc. You come home, your room is a mess. That's just the natural law of entropy. So that's when our particles are spread out. So it's a dispersal of particles, or they are just spread out. Oopsies, there we go. So if we have, with entropy, our units are going to be joules, Joules, for every mole times Kelvin. So a lot of times we'll deal with kilojoules. So you've got to convert between joules and kilojoules. You might also see this as joules per moles Kelvin, or joules times moles to the -1, K to the -1. Actually, I can get rid of that. You won't see that part of it. And we use the letter S to represent entropy or dispersal. So a positive S is thermodynamically favorable. Meaning nature tends towards disorder. It tends towards a greater amount of entropy. Negative S, so a smaller value, is not thermodynamically favorable. So I'm going to abbreviate that as thermofavorable. You will use the terms thermodynamically and not thermodynamically favorable as you're answering free response questions. So again, thermodynamically favorable is more disorder, and not or negative S is less disorder or more orderly. So when your room is a hot mess and your parents and guardians are asking you to clean it up, you can just say, hey, it's thermodynamically favorable, more disorder. You have to put energy in order to make it more orderly. You can say that, but then go ahead and clean your room, please. All right, so entropy increases when you are going from, like, let's say a solid to a gas, or even a liquid to a gas. Let's say you're going from even a solid to an aqueous solution. Maybe you're going from like 1 mole of something to like 2 moles of something. So when you increase the number of moles between your reactants and your products, there's probably going to be a few more that I'll add into here as well. Oh, if you like, pretty much if you spread out the particles. So think about gases. So let's just say spread out particles somehow. And this might be if you maybe increase the volume of a gas. Again, we'll play around with that. Entropy decreases when you do the opposite, when you go from a gas to a solid, or a gas to a liquid, or an aqueous solution to a solid. If we go for if we condense our particles and have a like synthesis reaction where we have like 2 moles of something and that's producing 1 mole of something. Maybe when you condense particles, so that might decrease the volume of a gas. So any of those. So we have several systems that we'll be dealing with today. We're going to figure out what happens to entropy in these systems. So we'll draw a model, we'll talk about a claim, give us some evidence, and some reasoning for here as well. That evidence reasoning part can kind of blur a little bit. All right, so we've got CO2 solid and CO2 gas. I'm just going to make myself a little key and say that that little dot represents CO2. So here I have one system, but at 2 different times. So the size of my container should remain the same. I have a solid, and the number of particles should stay the same as well. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 particles here. And they should be relatively the same size as one another within the solids and when they're spreading out as a gas. So the particle size does not change. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So let's think about this. Is this thermodynamically favorable or not? And so we will say this is thermodynamically favorable. I'm just going to write therm favorable. So for here, the particles are going from a solid to a gas. And the evidence, we're just showing what's happening. So particles spread apart. And we'll say solid to gas. So we can say for reasoning, there is more disorder. And there's an increase in entropy. And our delta S is positive. Cool, so that's how we would describe each of these. So let's take a look at number 2. We've got H2Cl2, and that produces 2 HCl, all of which are gaseous. So maybe oopsies, I should probably get them closer together. So maybe my H2 looks like this. Actually, you know what, let me just do a dot for H, an open circle for Cl. So here, I'm going to show that I have, again, 2 systems, a before and after. The size of the container, we're assuming, has not changed. So try to draw your boxes closer together in size than I have. And we have equimoles of them. But because these are diatomic, I'm going to show that they are together like that. So maybe I show 2 moles of H2 and 2 moles of Cl2. I'm going to break these bonds between the H2 and then between the Cl2 and then reform HCl. So now I've got these two combining together. All right. So let's think about this. Is this thermodynamically favorable? So I've taken essentially these particles that were, oh wait, so sorry, I have to do more because I have 1, 2, 3, 4, 1, 2, 3, 4. Oh no, I'm good. Okay, we're good. So essentially, we are thinking about if this is thermodynamically favorable or not. Because we have condensed them and we're showing that we are decreasing in the number of moles of those particles, we are going to say that this is not thermodynamically favorable. So again, we have 2 individual gases forming, you just write down, forming one gas. So we can say new bonds are formed. Two gases become one gas. And our delta S is negative. So that's not thermodynamically favorable. Let's go to the next page and take a look at some of these other examples. And I would highly encourage you, pause, try these on your own, see how you do, and then come back to me. Yeah, I'm assuming you're back. All right, cool. So that's N, that's O. So I'm going to show 2NO plus O2. Again, the same container, 2 different time periods. I'm showing N and O. And for every 2 of these, I have 1 O2. And then here I have 2 NO2 gas. So because we'll make N the central atom, so notice we go from 3 moles of a gas to 2 moles of a gas, similar to our, so essentially what's happening here, that this is probably not thermodynamically favorable. Our evidence is that we go from, let's see, 3 moles of a gas to 2 moles of a gas. All right, so we can say we have new bonds formed. Our, let's see, less dispersal of particles. And we can say that delta S is negative in this case. Right. For our KNO3 solid versus aqueous. So if we do this as our KNO3, we can show, oh, actually, no. This is a ion that's going to separate out, meaning that both K and NO3 are soluble. So let's keep them kind of like this. So I'll show as a solid, they're doing this. It's an ionic solid. But when they're in aqueous solution, they're going to completely disperse. So here, this is thermodynamically favorable. We go from a solid to an aqueous solution. So here, our ions separate in the solution. We have more dispersal. Our delta S is positive. All right, cool. So right over here, this time we are changing the pressure. So if the pressure changes, that is a direct result of our volume changing. We still have NO2 gas for each one of these, so I'm going to probably put it right over here. This is equal to NO2. Don't forget your key. So if this is my container, I'm going to show that I had that container. However, it's now cut smaller, meaning that this pressure increased because the volume very likely had decreased. So let's say I put in, let's see, 1, 2, 3, 4, 5 particles in here. They're all spread apart. Then we have 1, 2, 3, 4, and 5 particles here, which are more condensed. So this is not thermodynamically favorable. We say decrease in dispersal or less dispersal. The molecules are closer together. So here we could say as volume decreased, pressure increased, and the particles come closer together. We can say entropy decreased and delta S is negative. And then over here, we've got O2 gas at 273 Kelvin versus 298 Kelvin. We're assuming the same size of the container. So the only way to show this is showing that our particles might move around at a different rate. So here, 1, 2, 3, 4 particles. let's show that they're moving randomly. Here we've got 4 particles. But since it's a higher temperature, you're going to show more movement. So maybe we add that to the previous page. Entropy increases when temperature increases. And entropy decreases when temp decreases. So this is more thermodynamically favorable. The particles speed up, and we can say more random motion. Actually, I'm sorry, particles speed up as kinetic energy increases. So for the reasoning, and again, it's kind of blurred. Like evidence and reasoning and all of these have all kind of been part of the same thing. It's not a good example of QCER. For more random motion, the particles are more dispersed. Entropy increases. And you have a positive delta S. All right. So hopefully those were not too bad and kind of get the conceptual part of it. Now let's talk about some of the mathy things of it. So the equation for determining entropy in a reaction. This should hopefully look somewhat familiar. So I'm going to do, it's essentially very similar to like what we did with enthalpy. So we had products minus reactants. We're doing the same thing here, except this time we have delta S, standard conditions, 298 Kelvin, 1 mole of the substance. This is for the reaction, Rxn, is equal to, and then we have the sum of the moles of the delta S values of the products minus the sum of the moles times the delta S of the reactants. Again, looks a little scary, but you've done these before and you've done probably pretty well with these as well. So number 6, calculate the entropy change at 25 degrees Celsius in joules per Kelvin for the reaction below, given the data for entropy in the table. So we've got this information for entropy. And we're essentially going to do the moles of the products minus the moles of the reactants. So I've got 2 SO3. So I'm going to put these in, let's do brackets here for the product, excuse me. So I've got 2 times the value for SO3. So that's 256.6. These are all in joules per moles Kelvin. So I'm just going to kind of leave units out of it. Sorry. Actually, I shouldn't. So I'm going to show 2 moles here. And then I'm going to show joules and then Kelvin times mole, just to show you how those moles cancel. All right, so that's the product minus, and I'll neaten this up for this next one. Let's see, 2 moles of the SO2. So the SO2 is 248.1 joules over moles times Kelvin, canceling out the moles. That's this part, plus do the same exact thing for oxygen. There's 1 mole of oxygen times 205.3 joules over moles times Kelvin. Moles cancel. And then you're left with joules and Kelvin for the rest of these. All right. So 2 times 256.6 minus 2 times 248.1 plus 1 times, so plus 1, sorry, 205.3. Close out my parenthesis, and I end up getting negative 188.3. So make sure that you check this in your calculator, check me. Make sure you know how to put this into your calculator correctly. I screw these up all the time. So please take time to actually make sure it is all set. So this wants to know that we've got the entropy change here. This is negative. This is not thermodynamically favorable. I know it didn't ask it, but we're going to write it anyway. All right, cool. So 7. The delta S of the following reaction is, oh, they give you that. Determine the entropy value of I. So this whole reaction is going to be equal to 165.29 joules over moles Kelvin. So essentially that's what we found in the last problem. That's what this all this was equal to right over there. So we'll do the same thing over here. I'm going to spread this out a little bit because I know I'm going to need some space. 165.29 joules over Kelvin. I think that one probably should have been joules over Kelvin. Is equal to, and then let's do the products first. So I'm going to do those in brackets. 2 moles, and then of HI, 206.30 joules over moles times Kelvin. Cancel out your moles. Minus, all right, and then I've got my H2. So 1 mole of H2 times 130.58 joules over moles times Kelvin. And I know I keep saying moles and Kelvin and switch with what it's written there. It's all the same. Plus, there's only one of those. So that is my unknown. That's my X. All right. So we're just going to essentially do some algebra on this. Right? We have, get this in here. We're subtracting these two from one another. So I'm going to subtract this product from over here. 165.29, let me make sure my values are correct, minus 2 times 206.3. Notice that's in parentheses. That's a negative. This part's a negative. I'm going to just do negative second answer to make that positive. And then, so essentially what I want to do here is, I don't want to do that. Yeah, so I'm going to subtract out, if I'm adding both on this side, I'm going to subtract that from both sides. 5, 8. So again, I did that answer minus the 130.58. And again, you don't have to do the negative answer for that. I just like to get rid of some negatives wherever I can. So if you didn't, then you would have done positive or adding in 130.58 to both sides. So here I end up with X is equal to 116.73. And my units are joules over moles times Kelvin. And then, of course, we can always just double check to put that back into here. I'm just going to do that just to double check to make sure I did these things correctly. 30.58, cool. And then 2 times 206.3 minus second answer. Cool. Awesome. All right, I just need to double check that for my own sanity. Cool. So if you have any questions, by all means, just let me know. Take care. Bye.